Before we start, if you're enjoying these conversations, please make sure that you like or subscribe to Cleaning Up. It really helps other people to find us. Cleaning Up is brought to you by the Liebreich Foundation and the Gilardini Foundation. Hello, I'm Michael Liebreich, and this is Cleaning Up. By now, we've all heard of quantum computing, but what is it and what will be its impacts on the net zero transition? My guest today on Cleaning Up is Tommaso Demarie. He's the CEO and co-founder of Entropica Labs, a company working on the use of quantum computing to solve real-world problems. Please welcome Tom to Cleaning Up. So, Tom, very good to see you here.
It's great to be here. Thank you, Michael.
Now, Tom, tell me, where are you at the moment? Where are you dialing in from?
So right now I'm at home in Singapore, which has been my home for the last 8 years. In fact, I came here to work at the Center for Quantum Technologies at the National University, and I'm calling you from there.
And is Singapore a hotbed of quantum computing?
Great question. Singapore was very actually forward-looking from the beginning because they started the Center for Quantum Technologies more than 12 years ago. So it was really one of the hottest places to work in quantum computing, but also in quantum technologies altogether. So yes, absolutely. Especially in Asia, especially in this part of the world, is one of the best places if you're interested in quantum tech, or if you want to work in quantum tech.
So now we've got just under an hour and we've got a lot to cover. The audience, my audience, usually consists of people who basically know lots more than me. And also people who know relatively little, but they're all really smart. So we're going to have to do everything from get really into some of the detail, but actually we've got to start by saying, what is quantum computing? And, you know, what's the quick version, please, not the PhD version.
Sure. This is a question I love. It's a very hard question to answer, I tell you immediately, but let me try. So the quick and short and dirty answer is, quantum computing means processing information using quantum systems. Let me say a few more words about that. I guess everyone who's listening, and even you, is familiar with the idea of a computer, which is what we are using right now to do this call. So when you have a computer, what you're really doing, you're processing information. Quantum computer goes a step beyond that and touches on the quantum mechanical effects, so the fundamental effects, if you like, of nature, to do something more than classical computers can do. And everyone is very excited about the concept of quantum computing today because these devices, if you like, they bear the promise to solve some problems that are impossible to solve, or at least they would take a really, really long time to be solved using traditional or conventional or classical computers. I will use these words interchangeably. And they would be able, at least we believe, that they will be able to solve these problems much faster.
Now, is it just that they are faster? Are they kind of just like normal computers, but faster? And is it because, you know, a normal computer uses noughts and ones, and a quantum computer can use all the different quantum levels, and there's uncertainties and some, you know, sort of weird physics effects, but fundamentally they're just, think about them as just really fast computers? Or are they doing something different? Are they going to be modeling things because they are quantum computers? Can they sort of short circuit entire algorithms and do things in a much better way?
I'm glad you're asking that. So no, you should not just think of quantum computers as much faster classical computers or something like that. In fact, quantum computing is an entirely different paradigm of computation. I think there is something very profound about how, you know, humans learn more about nature and learn more about physical theories, and how the computing models and the computing paradigms also improve with this, you know, better understanding of physics. So after having, if you like, mastered classical physics, then classical computing in a way followed suit. And as I guess you know, in the 20s, in the 30s, quantum mechanics came to be last century. And that really sparked a revolution in our understanding of nature. And in the 80s, the concept and the idea of quantum computing was, if you like, was born or was introduced. So it's a different paradigm, and quantum computers can do things that classical computers cannot do because they can tap into effects that are intrinsically quantum mechanical. I can give you some names also for your audience. Maybe they're interested in learning more. For example, they might have heard of entanglement. They might have heard of superposition. They might have heard of interference. In fact, even the basic unit of information of a quantum computing is different. It's called a quantum bit, short qubit, while the traditional unit of information for classical computers is the bit. And I have a very nice analogy that always helps me to understand the difference between the bit and the quantum bit. And hopefully it will immediately give a little bit of understanding of why the two are different. You can think of a bit as a switch. It can only be on or off, like 0 or 1. And in fact, if you take planet Earth and your position on the planet is the same as a bit, then you could only be either at the North Pole, and then you would be in a 0 state, or you could only be at the South Pole, then you would be in a 1 state. But if you try to do the same and you want to describe a quantum bit, a qubit, then you can do so much more. In fact, you could be anywhere on the surface of the planet, absolutely anywhere. And that immediately should help you understand that quantum computers can access more computing power, if you allow me to say.
That's a great analogy. I'm going to use that because, what you've got is a situation where fundamentally with normal bits, it's binary, and you can teach it to really quite young kids, right, using, is there a jelly baby? Isn't there a jelly baby? It's actually quite easy. But with quantum, of course, it just is so non-intuitive that it becomes very difficult for me to envisage it and therefore to communicate it to anybody. But I'll use your analogy there.
Please.
But when you try and turn that into an actual thing, okay, so we all read these stories about quantum entanglement, and they take one particle however far away and so on. And then, if you come down to the actual computers, what does it look like? What physical systems are we using? I mean, there's different approaches, right? Optical, et cetera, et cetera. So what does it actually require in terms of, in a sense, the hardware?
Right. In fact, if you don't mind, before I answer the question, I also would like to say a few more words on why quantum computing is so fundamentally important and why I believe it's fair to be very excited about the technology. So in the 80s, in fact, in 1982, there was a conference organized by IBM, conference about computing, in fact. And Richard Feynman, the famous physicist, he said something incredibly profound. He highlighted the fact that nature is fundamentally quantum. And therefore, if you want to simulate nature in its entirety, ideally, you should use another quantum system to do so. But the conventional computers, the classical computers, are not quantum. So he had already understood, and he wasn't the only one, to be fair, he had already understood that classical computers have some fundamental limits. That as far as we can understand, as far as we know about physics, they are not able to efficiently simulate any other physical system, and there are also some problems that remain unsolvable for these machines. And I think it's very important to say that because it's also set the context right of the whole conversation. And I would also like to highlight how computing today is really the backbone of economy, right? The growth in computing power since I know this is an example that everyone uses, but since the Apollo landing on the moon and the computing power of the device that they use to guide the Apollo up to today, to the supercomputers that we have today, has been nothing short of incredible. And in fact, the more computing power we have, the more we can do as a society, the more problems we can solve, and the more we can grow altogether. But there are also limits, as I said, to what classical computers can do. And this is why it feels like there needs to be a transition, just like there was a transition from solving problems using, pen and paper, and then we introduced the analog computer and then the digital computer, and things change radically. Now it feels like we need to do another jump and go, not throw away the whole classical computing paradigm, which is incredibly successful. In fact, keep it as it is, but also use at the side quantum computers in this case. Oh. And since you were asked, if you want to.
So we're going to get on to some of those algorithms, some of the types of calculus that we can't do with traditional computers. But let's get back to just so my audience has an understanding of, if you walked into a room and there's a quantum computer there, what are you actually going to be looking at?
Right. And the reason why I was giving this long introduction is because at the very beginning of the history of computers, these machines were huge. Today, we're used to have a laptop, on the desk. We have like 2 or 3 computers in our pockets, maybe a smartwatch, maybe one iPhone, another phone for work or whatnot. So we have computers everywhere in our house. But at the beginning, this was not the case. They were very large machines, quite expensive. They were located in few places around the world. And people would go physically there to access them, or they would phone from very far away asking to do something. And today, quantum computers are very similar in spirit. I don't have a quantum computer at home. You are unlikely to have a quantum computer at home anytime soon. In fact, there are very few quantum computers today. I would say less than 30, or at least in that order of magnitude. Let's say less than 50 commercial quantum computers at least. And they're all fairly bulky. But what is very beautiful is that unlike traditional computers, there are in fact many different ways today you can build a quantum computer. If you go back to this idea of the qubit, which is at the end of the day a mathematical description, then a big question that people have been asking themselves after Feynman made that famous remark in the 80s was, how do we actually build a qubit? And you mentioned a few of these architectures. So today we have superconducting chips or superconducting qubits, we have trapped ions, we have photonics, qubits, and so forth. And if you like, we can get into the details of all these different architectures.
So basically, as soon as you've got a physical thing that is exhibiting quantum behavior, and as soon as you can trap it, keep it in the same place, and link it up to some other stuff around it, then you could build a quantum computer.
Very nice. Almost, but we are getting there. Yes. So a qubit is a 2-level quantum system. If people are familiar with physics, you can think of that as a spin, really. But think of it as a 2-level quantum system. Now, not all quantum systems are 2-level quantum systems. So you need to be able to find some that exhibit that kind of behavior. And as you said, you need to be able to control them exquisitely so. In fact, the problem with quantum systems is that they're very susceptible to noise. Nature has this habit of disturbing quantum systems all the time. So when people try to build a quantum computer, what they really want to do, they want to, let me use the word create, or they want to encode qubits into physical systems. Then they want to put these qubits into a system that shields them from all external noise. But at the same time, since it is a computer, you need to be able to access it. So there are always these 2 forces kind of fighting between each other. On one end, you want to close your system as much as you can and protect it. But on the other hand, you also have to open it because you need to interact with it and tell it what to do, because indeed it is a computer.
And so a lot of the challenge is you've got, you'll just have some bit of noise, some bit of solar radiation, whatever it is, that comes in and creates an extraneous, a wrong answer. You have to find that and correct it within the computer so that you're not coming out with the wrong answer. Is that how am I doing here? Because this is
doing great. You're absolutely doing great, and we are going in exactly in the right direction, and I'm very happy of that. But even before we get to the what you just mentioned is basically the idea of error correction. So errors are introduced into the quantum computation caused by all sort of effects. You want to be able to correct them faster than they actually happen. Today, we are still not really able to do that. It's incredibly difficult to perform error correction. You need hundreds, thousands, millions of qubits to perform it successfully. And maybe this is a good time in the conversation to start giving numbers and also, giving names to the different players in the industry. So what is happening today in quantum computing? You have very large players like IBM, Google, Microsoft, at some point also Honeywell, building these devices. And you have startups, although maybe calling them startups is a little bit unfair because they are very well funded and also fairly large in terms of manpower, also building these machines. And they're all following different approaches. So for example, IBM and Google are building what they're called superconducting quantum computers. There, what you do, you have a chip and you basically build what they're called artificial atoms. So you use traditional circuitry to create something that behaves like an atom, like this 2-level quantum system, when you cool it down at very, very low temperatures. In fact, temperatures that are lower than outer space, like few millikelvins. So you were asking, how does a quantum computer look like? In this case, it looks like a very big chandelier, which is just a refrigerator. And the chip is at the bottom of this big fridge. if you like, because you need to cool it down so that this macroscopical system starts to exhibit quantum mechanical, therefore microscopical effects.
And how many chandeliers do you need? Is that one chandelier per qubit or many qubits under one chandelier?
Many qubits under one chandelier, luckily. So there's been a lot of progress in that sense. We started with a handful of qubits. So in 2016, IBM put the first quantum computer on the cloud. And this is another very important word that I will be using a lot today, the cloud. So they put the first quantum chip on the cloud. It had 5 qubits inside a single chandelier. Today, or actually I should say a few weeks ago, IBM released a new device with 127 qubits, still in a single chandelier, which is incredibly impressive because in just a few years, we have witnessed what really is an exponential growth in the number of qubits.
Okay, now just for completeness, some of the startups, are they following the same, first of all, who are they? And are they following the same chandelier approach, the superconducting circuit, or are they choosing a different approach?
Some of them are following the same approach, some of them are following different approaches. So we have Rigetti. There is a company based in California, near San Francisco, in Berkeley. So they are also building superconducting quantum computers. They're also being very successful. They just announced a 40 and an 80 qubit device, still 40 and 80 qubit chips. These are 2 different chips. Each one has its own chandelier. But then you have other companies, for example, IonQ, that IPO'd just a few months ago, quite successfully, with a $2 billion valuation. They're building a different kind of quantum computer. And I would like to emphasize how actually beautiful this is, because in classical computing, pretty much all the devices follow, they're all the same, allow me to say. If you buy, if you buy a Mac, if you buy a Lenovo, they might have different architectures, but the fundamental idea, the physical realization doesn't really change. This is still not true in quantum computers. There are all these different competing architectures. And for example, IonQ is building what are called trap ions quantum computers, where what you do, instead of building artificial atoms, you use real atoms. You eliminate an electron, so they are ionized, so we call them ions, and then they send each single ion inside the vacuum chamber, and they keep them in place using electromagnetic fields and lasers, which is really incredible because when you look at the pictures, you can see this beautiful line of atoms perfectly aligned. Again, exquisite control of quantum systems.
Tom, I'm smiling because we had Stephen Chu, Professor Stephen Chu, former Secretary of Energy in the US, who of course won a Nobel Prize for trapping ions using a laser. And that was his innovation. But now we get them to line up and march in time with each other.
It's incredible. It's incredible. And another point that I would like to emphasize is that all these ideas, everything we're discussing right now, for example, the superconducting qubits, these are based on a particular kind of qubit called a transmon qubit, which is incredibly young because the idea comes from 2007, if I'm not wrong, from Yale University, Sholkopp's lab. In fact, one of the people who was the author of that paper is today one of the leaders in the IBM efforts, Jay Gambetta. So 2007 is really, really little, is literally yesterday.
Right.
And from the theoretical idea, if you like, and the first realization of a transmon qubit, today we have a device that is basically a commercial quantum computer. Is absolutely fantastic.
And just in terms of the tour of the different approaches, there are people working with photonics and saying that they will be less error prone because a photon doesn't interact in the same way that an ion does with all the stuff around it. Is that something that you give credence to?
So, right. If you remember before, we were talking about noise and how quantum systems are very susceptible to noise. What they say is true. So photons tend to interact with very, very little. So that is correct per se, that photonics chips or photonic quantum computers will be more noise resistant. And there are a few companies following this approach. For example, Xanadu in Canada, or PsiQuantum also in California. And they're following slightly different approaches, but they're both based on photonics. The difficulty there, though, is that, yes, they interact very little, therefore we have less noise, but they're also more difficult to manipulate because they interact very little. So you save on noise, but then you need to be incredibly smart to perform what are called quantum gates. So to perform operations on the qubits, on the photonic qubits.
Okay, so now let's talk about how many qubits you need to do something useful, because you're going to use some of them for error correction and so on. So what's the magic number, and how close are we to getting there?
Right. So let me remove from the conversation quantum annealers that are yet a different kind of beast in the universe of quantum computing. So D-Wave is a company following that approach. They have thousands of qubits, and I'll just say for completeness, but I will not be talking about them because the approach that they follow is slightly different. What we are talking about right now is called universal quantum computation. So everything I will be saying refers to this idea of being able to perform any computation you like with a quantum computer. The largest number of qubits available today is the 127 qubit device by IBM. Then you have Google. You have Rigetti with the 80 qubit device. Google with between 50 to 60. There is a device in China at the FA University that has 65 qubits, if I'm not wrong. And then you keep going down. You were asking how many qubits you need to do something useful. There's a great question, and the very, unfortunately, disappointing answer is that we don't know just yet. Because if you think of utility as, or at least if we assume the utility means being able to solve a problem that has commercial value, so a problem that somebody cares about, then a quantum computer hasn't been able yet to do so. Quantum computer so far has not solved a problem that has commercial value, that has commercial relevance, better than a classical computer can do.
So this is quantum supremacy, where you finally do something that you couldn't have done with a normal computer, and that has not happened yet.
Right. I was speaking about utility exactly to make that separation. So there are these two concepts that sound very similar, but in fact, they are subtly different. So what you refer to as quantum supremacy means being able to solve a problem, any problem, even some mathematical, very abstract problem, better than a classical computer. And in fact, that has happened already a few times.
Wait, so but it was not useful, or what?
It was not useful. It was not useful. Scientifically, maybe deserves a Nobel Prize. And it might at some point deserve a Nobel Prize because it was an incredible effort and an incredible result. In fact, this was done by the Google's team, led by John Martinez in 2019. They use a superconducting chip to solve a mathematical problem, what is called a sampling problem, where you try to sample from a probability distribution that is highly complex. And the assumption is that you wouldn't be able to sample from that distribution using a classical computer, or at least it would take a really long time. And when that happened, before the result was officially announced, actually the results were leaked to the press. So they were appearing everywhere on the internet. And at the time I was at a conference, and there were quite a few representatives of the Google team there, and everybody was like freaking out. And they were all asking, what happened? What happened? What happened? What happened? And the Google team was pretending that nothing had happened. And then 1 week later, the results were officially published. And it was, it was great. But as you said,
so that was a big deal, clearly.
It was a huge deal. This was a huge deal, because there are still today skeptics of the technology, people who say quantum computers will never work. But I think at this point in time, they are just, allow me to say, being a bit delusional.
So why has it not been possible to do anything useful with it?
Because classical computers are incredibly good at what they do. So if classical computers wouldn't exist, then we would be talking about a revolutionary technology, which in itself is a revolutionary technology. But the reality is that quantum computers, the challenge is against classical computers. So you have to remember that classical computers are incredibly powerful. Like the newest Japanese device, the Fugaku, it is huge. It has 500,000 teraflops. It is just an incredible, like the computing power that these machines have is incredible. So before we can actually reach those limits, we still have to push the boundaries of what quantum computers really can do.
Okay. And talk to me about how will you actually use this? So it's somewhere more than 127 qubits, but it's not like It's not like we're 20 years away. I mean, we're getting close, right?
I believe so. Yes. I don't think we're 20 years away. Yeah.
Right. And how will the industry be structured? I want to get on to how it might have impacts in, the area I know well, the net zero transition.
Mm-hmm.
But let's first talk about how you actually access these machines. I mean, you've got this chandelier. You're not going to have one in every, in every office. It's probably, if I've understood it right, they're probably so difficult to handle. They're never going to end up, in your mobile phone or in your car. They're going to sit somewhere, at least for the next, they're going to arrive on the scene commercially in the next few years. But for the next many decades, they're going to be big centralized things. What does the industry look like to enable them to be used? You talked about the cloud. Is that it?
Exactly. So the cloud is really the key word here. Take the chandelier, and you're right, they're still fairly complex to move and to handle. But funny enough, IBM started to ship them around the world. So they have one in Japan, they have one in Germany, and most of them are in Yorktown in US. So even there's a lot of progress. So it's becoming easier to move the machines around. But yes, for now, they are sitting within the cloud infrastructure of one of these big companies. I mentioned IBM a few times, but AWS and Microsoft have also started their own quantum cloud services. For now, they're not giving access to their own device, to their own proprietary devices, but they're giving access, for example, to Rigetti's, IonQ's devices, and others. So you have these central players, if you like, these quantum cloud providers, who ideally want to give you or should give you access to both the classical computing power and also the quantum computing power. And if you're the user, let's say if you're me or my team at Entropica Labs, what we do is we connect through the cloud to these devices, and then we send what we call quantum programs or quantum algorithms that can be run on the machines. And then we wait for the results to come back.
Okay. So, but you're not sending, I mean, it's not running, I don't know, your call center software. It's not running your normal sort of computer programs, because classical computing is doing all of that. But what you're doing is you're identifying a particular algorithm, folding a protein, or doing some vast forecast that the classical computer can't do. You separate that off and you're sending just that to the quantum computer. Is that correct?
This is one way to think about it, yes. And you very correctly, you said something very important, right? Which is you cannot just take your code, let's call it your classical code, whatever code you might have, send it to a quantum computer and hope that it will work, because it is not going to work. The paradigm is different, the logic is different. In fact, even when I speak about our company, it's very easy to say that we are a quantum software company because we don't build quantum hardware, but I'm very uncomfortable with that word, software, because I personally believe that software in quantum computing is still mostly lacking, but it's lacking simply because we never needed it, because we didn't have quantum computers on the cloud. So this is a whole new industry that is growing very, very quickly. And we are starting to realize what is actually missing in terms of hardware, infrastructure, and software needs. And people are filling gaps, et cetera, et cetera. And to give more meat to what you were saying, like we work in optimization. So applied mathematics, ideally you have these complex problems, you want to find the ideal configuration that either minimizes or maximizes some cost function of interest for you. So what you want to do, you want to find the mathematical description of the problem, and you want to rewrite it so that you can encode it into the logic of the quantum computer. And then you interface with the quantum computer of your choice. And remember that we have different devices available. So there is still quite a lot of work needed to interface with the different machines. Then you send the code and you wait for the result to come back.
So I think when we first spoke, or one of our early conversations, you talked about a typical algorithm might be inverting a matrix, something that's incredibly computationally intense and might take a classical computer, if it had a big enough matrix, to take thousands of years. So you just send that to the quantum computer, then you get the results back, and you kind of then go off and continue doing whatever it was, optimizing your power network or whatever, using the results.
So that could be one way to do it. And I'm emphasizing the fact that it could be one way to do it, because the reality is that people are proposing different approaches to how we will be using quantum computers. So inverting a matrix is something that becomes very, very important when you want to solve linear systems, for example. So in engineering, in data science, in machine learning, this is a fundamental problem. And yes, it can be very complex if the matrix is very large. So you could imagine in the future, and I'm saying in the future because to solve that problem, you need most likely millions of qubits. So we're still very, very far away from being able to handle it in practice. What you could do, you could have a workflow where most of the computation actually happens on a classical computer. And then once you have the matrix, once you have the information, you pass that to the quantum computer using a particular architecture that's still missing called a quantum RAM, a quantum random access memory. You do what you need to do, you extract a piece of information of interest from that computation, you return it to the classical computer, and you continue with your workflow. That could be one way to do it. If you are thinking about quantum simulations, for example, quantum chemistry, material science, then it becomes even more complex because it's still unclear how much of that computation is to run on a classical computer, how much of that computation is to run on a quantum computer, because again, these are hard regimes to explore.
So you may actually have a model of a molecule or molecular interactions in the quantum in the quantum computer. So then, now, the question I'd have there though is, how do you check your maths? Because you send something off and it comes back and it says, right, this drug will interact and will do this. And you say, well, how do you know? And it'll say, well, because I'm a quantum computer. And you have no way of knowing whether that is in fact the case. Or do you? Is there a way of sort of, I don't know, using other quantum computers to check each other's maths?
It turns out this is actually a huge problem, because if a quantum computer can solve problems that a classical computer cannot solve, then if a quantum computer in the future gives you an answer, you cannot rely on your trustworthy classical computer to check it because it cannot derive the same answer. So what do? There's actually a problem called verification of quantum computation. And if you assume, and let's say is a fair assumption, the quantum mechanics is correct, then what you want to ensure is that the quantum computer is actually doing what you're asking it to do, or that the quantum cloud provider is indeed giving you access to a quantum computer, not to some bogus machine of sort. So yeah, you mentioned something that reminds me very much of a work I was part of a collaboration I was part of that was published a few months ago, where indeed we use different quantum computers to check each other. Now that we have more quantum computers available, then it seems quite a reasonable idea to use each device to check each other and, convince ourselves that they're actually doing what they should be doing.
I'm just reminded of a time when I think it was one of the Intel chips did a particular thing, and I don't know if it rounded down or it did something, and it actually came up with wrong answers, and it took a long time to figure out what was going on. I don't know if you're familiar with this situation. It sounds like that, but on steroids.
Yes, absolutely, because that is an even more subtle problem. But here we're really talking about devices that unfortunately are still suffering from all sort of noises, so all different issues, if you like. So yeah, you can say there is something very similar on steroid.
Okay, so now with that all as the preamble and the caveat and how hard it is and where we are and so on, the transition to net zero, there are all sorts of problems that I could imagine might yield to this phenomenal new computing power, whether it's within the chemistry or the network modeling or all sorts of things. Are there any that you would sort of pull out and say, yes, I could see how quantum computer is going to revolutionize this or that aspect of the net zero transition? I don't know. Anything come to mind, or I could suggest a few?
Quite a few actually come to mind. And that's another reason why I am personally very excited about quantum computing as a technology. Maybe we can start with this division. We can categorize problems into two sets of problems. Problems that are very natural to quantum computers. So let me say that they are grounded on concepts of quantum physics and quantum mechanics, and problems that are not quantum per se, but they rely on basically very complex systems. So you're trying to solve applied mathematics problem with a very high degree of complexity. So in the first category, in the former category, you would have quantum chemistry molecular simulations, material science, and those have, as you can easily imagine, a lot of applications into the
right. So things like enzyme reactions, battery chemistry, catalysts, in the battery cathode and anode,
photovoltaic.
also exactly. So surface effects in photovoltaics,
Absolutely.
where there's something quantum going on,
Yeah.
and therefore trying to break it down into a linear classical computing ones and noughts is just simply not going to capture all the things that are going on at the same time.
Correct. So if you want to fully understand the properties of quantum systems, intrinsically you need a quantum computer. You need another quantum system to capture those properties fully. And you mentioned fantastic use cases, right? Especially for me, something that I find very, very powerful is this idea of batteries. Now we are witnessing this transition, if you like, to having incredibly good, let me just say the word good, incredibly good batteries. And this is one of the reasons why we're also witnessing this transition to electric vehicles, because now we can actually keep a car with a battery that lasts long enough, that can be quickly recharged. And before this was not possible. So imagine a future where we can improve on that even further, where we can actually increase the capacity of the battery, where we can increase the lifespan of a battery, where we can start miniaturize the battery. That enables, not only it helps with reducing, emissions, and it helps with the whole idea of climate change, but it also enables new technologies that today are just hard, especially in transportation, especially in production, and also in grid management of the energy grid.
That's right. And it's a sort of dirty secret in some of those sectors, how much trial and error is still required. Just formulating different bits of the battery or different combinations of. I mean, it's the same in the drugs industry, isn't it? The same in the medical industry. There's a much more trial and error than you're led to believe by watching Hollywood films, right?
Yeah, absolutely. So the problem is that in chemistry and in material science, the worst cases in simulation might require exponential resources in terms of computing power, which means that if you want to fully simulate the system, it will take too long, just potentially thousands, if not longer, of years. And you want exactly to avoid the problem that you're mentioning, trial and errors, lab trial and errors, and you want to move as much as you can of that process, let's say on silicon, in this case on quantum computation, so that then you can only go and test what you're already fairly sure is going to work.
And are we already seeing companies trying to do this? I mean, the computers aren't quite ready for prime time, but are we already seeing the big chemicals companies, the Dows and the BASFs and so on? I mean, I don't want you to reveal who your clients are, but do they include, or do you see the big chemical companies, the big material science companies, getting actively involved now in quantum computing?
Right. So absolutely. And you see, in fact, it's very interesting. You see more than that. You see the quantum hardware companies, you see the startups, and you see the chemical companies, say the big companies interested in these applications, all working together. It's still a very collaborative ecosystem, I would say. So you have, for example, Microsoft Station Q, which is a research center sponsored by Microsoft in California. They've been doing incredible work in 2017 on nitrogen fixation.
Okay,
just to give you an example.
Right. Nitrogen fixation, of course, is that would be a huge problem to solve for the climate, because at the moment we use nitrogen in fertilizers, and I think it's 2% of global emissions comes from making fertilizers from natural gas and even from coal. So we make the hydrogen even from coal. So fixing nitrogen from the air in a clever way would be huge.
Right. So exactly, it is exactly. So I think is about between 1 or 2% of energy consumption globally. It goes to to perform nitrogen fixation, because you want to have nitrogen basically assume a biological processable form, right? Using catalysts. And what is incredibly fascinating about this problem is that nature knows how to solve it, because plants, bacteria, they do that. It's just that it's incredibly hard to find the right catalysts, or catalysts that are very efficient for our needs, because it's just a hard problem. There are too many. You can't practically test all of them. So you eventually, if you want to improve the process as it is done today, you need to rely on computation. And in this case, quantum computing is going to help.
So the question of nitrogen fixation, of course, there's a parallel problem around carbon fixation. If we could take carbon out of the atmosphere in an incredibly elegant and clever way, I mean, the thermodynamics of carbon is very different from thermodynamics of taking nitrogen out, because it's 400 parts per million versus 80% of the air, or whatever nitrogen is. But that feels like an analogous problem, no?
It is, and funny enough, Microsoft is also looking at that. They released a paper just recently where they're talking about CO2 fixation. And again, the idea is very analogous, right? They are looking for quantum algorithms so that they can find better catalysts for CO2 fixation.
Right.
And also in terms of carbon capture, since you mentioned that, there was a recent collaboration announced by Total together with a startup called, at the time was called Cambridge Quantum Computing. Today it merged with Honeywell Quantum Solutions, and they're called Quantinum. But this is just to say that it is not only Microsoft, there's not only these big players, but as you were mentioning, is also the big companies together with startups looking at innovative solutions for these problems using quantum computing.
Okay, so those are examples of processors that are inherently quantum.
Right.
So it's materials, it's chemicals, it's batteries, it's surface surface interactions on solar cells, and those ones. You reckon you've kind of got to go quantum because they're just the nature of the problem. But you said that there was another one where you're going to use the quantum computer almost as a kind of bigger sledgehammer for problems that are fundamentally, accessible to binary processing, but it would just take too long or be too difficult. Can you give some examples of those?
Sure. Yeah, exactly. I think of those as applied mathematics, let's say again on steroids. So I think the key word there is really complexity. So these are intrinsically very complex problems, and they happen in optimization, which is the field we focus on, but also in data analysis, in machine learning, artificial intelligence, and fluid dynamics, or weather forecasting, and so forth. So I'll give you an example that I think is incredibly interesting. Speaking about transition to renewable energies. So now that the prices both of basically solar production and wind production have been quite amazingly collapsing, pretty much an exponential rate in the last 10 years by, I believe, between 80 to 90%, at least for solar cells. It's not crazy to imagine that in the near term, we're going to see big changes in the electric grid, in the way the electric grid is designed. In fact, this was something that Noah Smith recently discussed also in his blog. If you don't know the blog, you should follow it. It's really interesting.
No opinion. NOAH opinion. Yes.
Correct. Yeah. Correct. So you can imagine that you're going to have an electric grid that is going to be very different from the one that we have today, potentially, where there will be a lot of smaller producers rather than having a big coal plant in the middle that is giving electricity to all the nodes. Each node might be producing electricity independently. But if these nodes are producing electricity based on renewable energies or renewable sources, then you have stochasticity in the process, because if it's cloudy, if there's no wind, then you're not going to be able to produce electricity on that time. So you need to be able to optimize this huge problem where you want to have a flow of basically, you want to have power on the full grid constantly, because everyone wants to have electricity available, right, at each point in time. But you need to do so by basically optimizing over a very large number of points, each one producing electricity in a stochastic manner. This is a huge optimization problem. Now, classical computers might be able to handle it. We don't know, but it seems to be quite a nice problem for, quantum computing in this case.
Now, we could disappear down this rabbit hole because there is an alternative approach there. And, I love that Noah is now applying his fabulous mind to this stuff. But there is an alternative approach, which is to have the nodes talk to each other and react like a flock of birds to what's happening around them, rather than having a single central supercontrol, which would have to be more powerful than any computer that already exists. And, this would be the transactive grid. which, I don't want to sort of pull rank, but I've been trying to get my head around for since about 2008. And you see elements of it. And the answer is going to be, you're going to see elements of both. You're going to see probably the big grid, the transmission grid, centrally controlled, and the distribution grids. But when it gets out to the edges, you have to have the washing machine talking to the other appliances in the house, not having that solved by even a quantum computer in Houston, and then trying to send the message back through the system, I think is going to be very difficult.
You're absolutely right. This is one of the reasons why I love optimization, because sometimes you're able to tackle very complex problems using very smart heuristics. For example, instead of looking at the global problem, it might be enough to look at the local problems, or break it down into local problems and find good solutions. But I think what you said is very real. You have edge problems, but you also have global problems that more likely than not are going to require the high level of computing power to be tackled.
No, absolutely. And I don't want to push back against the concept of the quantum computer in the optimization role there. And another one that would come to mind clearly would be the transportation system, where you do actually have quite a lot of central control and communication, even optimizing London's traffic light system. If I told you how primitive it is today, I was on the board of Transport for London, and I thought that there was some magic. It's not magic. It's still a lot of engineers going around, and not quite with stopwatches, but it's certainly not being done in the way that a quantum computer, in theory, could sit across it and do.
I'll give you, since we're speaking about transportation, I'll give you another interesting problem there, which is the whole idea of electric vehicles grids optimization. So if you have a limited number of stations, for example, where you can charge your EV, and you have a very large number of electric vehicles moving around, you want to be able to find, first of all, you want to be able to position the charging points in the right places. So this is a design, if you like, problem at the beginning. It's like a planning problem. And then you have the scheduling problem, which I believe is what you were referring to. Like once the vehicles are moving, you might want to have something telling you where to go to charge the vehicle, for how long, et cetera, et cetera. So it's just, I find it incredibly interesting to think about these very complex optimization problems that very quickly pop up pretty much everywhere once you start to have a very large grid with a lot of moving nodes and with a lot of stochasticity. So with a lot of, let's say, randomness intrinsic. In fact, I think it's also important to mention that there's an organization or consortium, I think is the right word, called Q for Climate, which brings together different scientists and experts, both from startups and universities or academic institutions. That is also looking at this kind of problems, in chemistry, in optimization, also in quantum sensing, for example.
Well, that's fabulous. And what we'll do is we'll put a link into the show notes, because I wasn't aware of Q for Climate, and it sounds like I should have been, but I wasn't. So let's try and diffuse that knowledge as well. I've got to ask you this. We've been through the kind of, there's the sunlit uplands. We will be solving chemical problems and quantum problems. We'll be doing this huge sledgehammer optimization problems. But is there a concern that the first quantum computer will actually be used just to crack the code and break the security on all of the infrastructure, all of the energy and transportation passwords out there? So, is there a risk that the first impact of quantum computing on the infrastructure and energy, transport, climate will be massively negative? A huge amount of investment required to protect against somebody using quantum computing?
Well, there certainly is a risk. In fact, you're referring to the infamous and famous Shor's algorithm. So this is from 1995. Is one of the very first, maybe the first quantum algorithm that had a real world application. Unfortunately, not necessarily a quote unquote good one. And this quantum algorithm can be used on a quantum computer of sufficient size. And again, we're speaking of millions of qubits. So something that is still fairly far away in the future, to crack RSA. And RSA,
which is the encryption algorithm.
Correct.
Yeah.
It's like a public key distribution that is used ubiquitously on the internet today. So usually when you connect to your bank or to your email account, you are communicating securely with the server through a variation of RSA.
Right, or to your power station, or to your
power
electric
station.
vehicle,
Yeah.
or to your transmission grid, your high voltage grid. I mean, it's being used to secure everything.
Correct. Pretty much everything. Now, yes, there is a threat. Let's call it this quantum threat. That if somebody somewhere right now had a quantum computer of sufficient power, yeah, they could crack all these codes, and it would be very hard for us to know that this is happening if they're smart about it. I don't believe this is happening. And in fact, I believe that the knowledge that this was the first application, or the first well-known application of quantum computing, this knowledge, in fact, I think has been way more positive than it may be negative in the future. And let me say why. Because it pushed the field forward. So it transformed quantum computing into what was, at the time, it really was more of some sort of curiosity, some sort of computer science niche topic that people were looking at. But once people became aware that it actually had a huge application, this completely changed the game. And companies, governments started to pour more and more money up until today. So the fact that everyone is aware that this is an application of quantum computing, I actually think is a very positive thing. First of all, because it forces everyone to be very open and transparent about what they're doing, but also because it forces companies and standard makers to prepare for a threat. And everybody knows about it.
So every digital technology that takes off has applications in one of two areas. One is security, and the other, of course, is pornography. But I don't see quantum computing being much use there. Maybe I'm wrong. Some clever soul will come up with something. But the point about it being a potential threat, and that focuses the mind, so that has sucked in a lot of resources. Presumably every CTO, CIO, Chief Information Officer, had to have a view as to whether it was going to render security inoperable. But does that also mean that there's some enormous arms race between not just companies, but also between countries for quantum superiority, not over classical computing, but using the words in a different way, superiority over each other?
Sure, there is. Yeah, there is. And it's also important to keep in mind that quantum takes, which is what we are discussing, but quantum also gives. So yes, there is a threat, but and governments, countries are aware of that, and there certainly is, let's call it an arm race between the US, Europe, and China, where they're all rushing to build more and more powerful quantum computers before the other countries or blocks do. But there is also an effort in building new infrastructures based on quantum communication, for example, also based on quantum computing, where you're able to perform certain cryptographic protocols, certain security protocols in a way that you wouldn't be able to do with classical, either communication or classical computers, with much higher security, if not complete security. Although complete security in cryptography is always a very theoretical concept that doesn't hold in reality. But I really love this concept that quantum takes, but also quantum gives. Like quantum key distribution is an idea similar to RSA in spirit, based on entanglement, the effect that we mentioned briefly at the beginning of the conversation, that allows you to exchange a key between two parties in a way that is basically unbreakable, in the sense that if somebody is eavesdropping, is listening to this key exchange, the two parties will be able to detect it and immediately stop the communication.
And this is presumably to do with Heisenberg and all sorts of clever quantum physics, that if somebody listens in, it changes the nature of the algorithm, of the calculation.
Right, so it has to do with the collapse of the wave function. It also has to do, it really is based on the very funky properties of entanglement that allows you to do something that you can't do with classical correlations.
Very cool. I need to stop there because you're going to lose me, but we're also nearly out of time, Tom, and it's been absolutely fascinating. I want you to just finish, if you might. If we were having this conversation, and hopefully we will be in 5 years' time, can you tell me what we might have seen? What would have been, what is it that you think is so close to happening that in 5 years' time, you'll be able to say, Michael, I told you this would happen, and it did?
I hope that it will be quantum advantage, what you were asking me about before. The demonstration that a quantum computer solves a problem of value, whatever value means, in a way that a classical computer is unable to do. I think we are very close to that. The biggest transition that we have enjoyed in the last really 10 years is that these machines moved from being, again, university curiosities. Curiosity is an exaggeration. University endeavors to commercial devices that anyone can access, that a teenager can access and start playing around with. And with his, so we are really living this stage or this time in the industry where people are trying all sort of stuff. Is the heuristic stage of quantum computing, if you like. And I believe that there is a very high probability, there's a real chance that by having access to these machines, by pushing the limits of what they can do, by trying smart and clever algorithms, we will be able to find a niche application where quantum computers can exhibit quantum advantage. Whether it's going to happen in the next 5 years, well, we don't know. Nobody really knows. But if you ask me, could it happen? And in 5 years, we will be talking about that and we will be very excited. Yes, I think it can happen.
Very good. So here's hoping that not only will quantum computing have solved its first real world problem, but that solution will actually also help us move towards net zero rather than some other less vital aspect of the economy.
Absolutely.
Very good. Listen, it's been a great pleasure talking to you, Tom. Thank you very much for spending some time with me. I know it's very late over in Singapore. And so I'm going to thank you on behalf of all of our listeners and our viewers. And go. Thank you.
It has been my great pleasure. Thank you so much, Michael.
So that was Tom Demarie, CEO and co-founder of Entropica Labs and quite the expert on quantum computing. My guest next week is Inga Anderson. She's an Undersecretary General of the United Nations, and she's the Executive Director of the United Nations Environment Programme. Please join me at this time next week for a conversation with Inga Anderson. Cleaning Up is brought to you by the Liebreich Foundation and the Gilardini Foundation.